Yeah, let us begin. So basically how the internet works is everything is connected to basically payloads and headers. So that's packets basically. And each packet has a header and a payload. The payload is the information, whereas the header is like the email it's like the address. So like when you're sending a mail, like a physical mail to someone, you have to put, the final address of where you want it to go, but it still contains your home address as well as actually, because when you send it, you have, in case you're sending it through your home address. So in case they have to return it, so it has the home and the starting address as well as the ending address. So that's what you can consider the header as. It's basically just a list, the starting and the final address for a node. And this is a packet. So, and then, basically for internet addresses, all URLs that you have are converted into IPv4. In this case, we have a random example here, which is 128.947 etc. Basically, it goes through a DNS, which converts the URLs into the IPv4 numbers that are understood for browsers to work. Basically, let's say you have Google. Google has its own IP address, whereas you have your own IP address. And if you type Google, your browser doesn't understand Google, so it has to first converts Google into an IP address and then bounces off the necessary nodes to reach the IP address of Google. And if you want to find IP addresses, converts URLs to IP addresses, we have a few links here that if you want, you can use to figure out the information. Next. So yeah, this is how this is a picture of how the internet, the packet traversal works. Basically, you have the source address here. Source node, sorry, which is basically you, and then this is Google. And then when you send the information, it goes, based on the reading of the header, it goes from node to node and each node knows the origination and the destination of the packet. So who sent it and then where it's going to go. So all nodes can keep track of this information, which is how it works in normal situation. And as it says here, they can take different routes. It just depending on what nodes are available and things of that sort. It could sometimes go through 62 nodes, or it could go through a lot less nodes. So it just depends on a whole bunch of factors basically to decide how a packet goes from your, I guess, desktop to the website that you want it to go to. And yeah, so this is a breakdown of how the links work, which is here you have the ones that the links that we go to, like Facebook, Google, any other social media, Netflix's etc. And .com basically covers all of it. It goes through the safe, the non-safe. It works in all situations. Whereas the thing that we're going to cover today, which is onion websites, are also work in all these situations, but you'll see the difference down the line, which is where basically onion links give you access to more than .com links, because in the best way they're less secure, but they also can contain more information because of that. And yeah, so this is where the different websites stand in the whole spectrum of things. And then, so Tor. Getting to Tor is a browser that we use that has a different traversal method of nodes. So when you start off at your home website, I guess, if you want to go to the final address, then you can, instead of traveling through normal nodes, which can be read by anyone, you traverse through Tor nodes, which protect the information comparatively, so that any person in the process will not know where you're going except the start and the final node. You will see more about this here. So basically, as we said before, the packets have two parts: the header, the payload. And the payload is the information. And even if the payload is encrypted, let's say you have encrypted information, the header is not. So it gives all nodes can read this information because of that, because they know, because it's not encrypted. It's only the payload that's encrypted. So anything that goes through those nodes can be read easily by everyone. And that's not something we need in if you're trying to have a secure conversation, because then any interested party can just tap in and see what what messages you're sending or what information is going through, and anything else that they want to know about it can be sent through here. It can be read through these midway nodes, which is, I guess, the problem in this situation. And this can be seen here, where you can see where you can see the receiving node. So the node that is sending, as well as the different nodes that it's going through. From source to destination, all of the nodes, you can basically see it in this list. If you basically ask for it, you get the information in an open area, which is not something that you want when you're trying to protect information, which is why we use Tor Browser, because it has its own private nodes that others cannot break into per se. They can have nodes in the middle that they control, but if they do control those nodes, they won't get the full information because you're encrypting everything rather than just the packet and leaving the header open for everyone. And that's the solution that Tor Browser provides, which helps solve some of the basic issues with security and things of that sort. So Tor was developed by the U.S. Navy to protect internet communications. This was developed some time back. And it's basically, the development is continuing with U.S. funding. They're still developing it. There's ways. It's basically being used as a method to protect people in situations where where they're either being censored or things of that sort. And also can be used to best way to explain it's much safer than using a normal website. So in scenarios where you need private communications from people in different nations to the US for government purposes, then you can potentially use the Tor browser to protect it, even though because it's more encrypted than previously known methods, which is the website. So, for example, it's pretty well protected because in 2014, Russia offered a bounty to crack Tor browser because they were having some issues with people organizing against the government, against the Russian government. So they put out a bounty so that people can work towards potentially breaking the Tor browser, which, it's it's still open to people if you want to try. So this basically shows that it's a pretty strong security mechanism in Tor, so that it cannot be broken into easily. And then it takes, it basically can be broken into, so it encrypts your information pretty well. And the basics here. Before we saw the information travel from one node, we saw the traversal in gray, which is through open nodes for anyone. Anyone can see. You have all the header nodes available. Even if the payload is encrypted, you can see it because you have the header. So it's basically, the gray is the complete open communication system, whereas red is where the red lines are the traversal through Tor nodes. where it basically protects your information, because these have an onion layering system which prevents not just the payload but also the header from being visible to all of the nodes. So if someone is in node here, they won't be able to see who the destination is, but they'll be able to see what the starter is. So this way you will be able to protect your information completely. Whereas here you will know this node as well as this node. So this is just a mechanism to protect information. And this can be seen here where you're encrypting the entire header and the payload in different levels, so that it can travel through different nodes. So for example, here you have list of nodes, T29, basically T for Tor, and then these X amount of nodes, and then it bounces off of these nodes to reach the destination node from the source. And the whole setup can be seen here. Previously, this header would have source dash destination, and then it would have the payload. But here, what they did was to protect that was you have the source here, and it just has the destination as the first node. So the packet goes from here to here, and this node does not know what happens to the packet after it goes to the next node. It just knows that once it reaches here, it decrypts, and then it sees, okay, the header says it has to go from T29 to T233, but it does not know what will happen to the packet once it reaches T233. So only once the packet eventually reaches T233 can it decrypt and then see, okay, it's going to go to T5. So this way you can protect the information that's in the payload by only giving them the information that they need to know. It's basically on a need to know basis of information. You're in the source node. Okay, from source you go to the first node, and then the second node knows only the first and the third node. Third node knows, second and fourth node. So this is how you can basically traverse this system. And yeah, this is the step process of how it just goes through and then reaches the destination node. And basically, in case this is the path back, in case, for example, you can act in case, for example, if the packet arrives out of order, then the packet in the destination has to put all of the packet. Basically, okay, so packets can arrive at the destination out of order. It's up to the destination node to correctly combine these packets. And so if a packet is missing, the source node has to be notified, and a copy of the packet needs to be resent. And this is the path back, basically. So in case it reaches the node 5, the destination node, and then it doesn't understand, or if something is missing, then it has to go back the same path. And at each level, so it sets up, okay, this is the destination, it needs to go T16, and then it encrypts it itself. And then that's what the nodes do. Just keep encrypting the information down from the bottom, from the destination, all the way to the source node. So, origin node access list of Tor nodes and create the packet. Basically starts by creating a packet of header, payload, and header, and then it keeps going to the destination in a zigzag route as we saw above. And then, so that's why it's called onion routing, because at every stage it adds an extra layer of encryption that is peeled off to view the next header, which shows where it has to go. That's why it's like an onion, as at every node, just a layer gets taken off. And as another important situation here is, in the final packet, it contains the header with the original source node, and the first Tor node is identified. And the reason being is because if the node in the destination node needs to send a packet back to the source node, then it has to know what the source node is. It knows two things. It knows the source node as well as the node before it. So in this situation, it would be T16. So it will know, okay, this is the source node. This is T16. This is what has to be in the header. This is what in the payload. I don't know the information, so let me send it back. But it sends to T16, but knowing that it'll eventually end up in the source node. And the list of Tor nodes periodically changes for security reasons, so that somebody cannot break into one node and then track the information. And how I guess governments and other entities try to break in is by trying to break into one of these nodes. So in this path, for example, if I break into node T233, I will know, okay, I got the node from T29 and T5. Then I can break it all the way through, trying to get to the final node. So to change this, they keep changing the nodes, so that one time you might have to go to T5, whereas next time, instead of going to T5, you go to T16, then to T5, then to the destination node. That's not the solution, but that's how you can, I guess that's how the Tor helps throw people off, is the best way to explain it. It helps prevention in spying on what you're saying. But yeah, so best way to explain it is it prevents in the process. Let's say you send a mail, it prevents someone from snooping in the process of the handoff. So that's basically what it's trying to do. And yeah, the route is changed completely. And as said here, it's not foolproof. Basically, if a non-Tor browser opened within a Tor browser, security measures of void basically go back to direct routing. So it basically just, if you open up a normal website, it just goes through normally. Like, it doesn't need to use Tor browsers, but someone monitoring the source and destination nodes may note synchronization of packets being sent and received. So basically what the second bullet point means is, if you keep sending the same destination node from the source node, you can eventually track it to understand, okay, who's sending and how this is happening. And that's why a lot of front websites are put up by the government, basically, that do some illegal activity where to catch you, because the destination node has also the source node. You can, if you create the destination node, which is the website or whatever that you have, then you will be able to figure out who is in the source node, and you can, using patterns, figure out, okay, it's XYZ person. And the best way to go against this is to increase the traffic, because the more paths there are taken and the more routes that are used, the less it can be properly tracked. So that's why the best way is to avoid traffic. And .onion, basically .onion is the links that we're going to use. Normally use .gov, .edu, .com, .something, .net. Whereas for the Tor browser, you would use a .onion site. And these cannot be searched on a normal website. So browser, sorry. So if you go to Internet Explorer, if you go to Chrome, .onion sites cannot be loaded. And so that's why they're safer and more protected, and you have to go through the Tor browser. So Onion IP addresses are not listed in the DNS. So you need the Tor browser to translate between .onion and the internet addresses to be recognized by the DNS. Let's say for some odd reason Google is protected behind, and Google has its own Onion link, for example. And let's say you want to go to Google, it has to go, you put the Onion address for Google, and then it then converts it back to the internet address, which is an IP address, which is then understood by the DNS, and then it's shown to you when you send an Onion address. This way, so this is how onions work. You cannot be accessed in a normal setting, and they're not listed in the DNS. And this is an Onion link. It cannot. If you type this in Chrome, it won't load. Whereas if you type the same thing in a Tor browser, it'll load. But it'll load. Now, if you enter the same link, which is any link, for example, in Chrome and Tor, you'll see some differences. I think Tor restricts some JavaScript that you send, so it prevents you from, certain things you can't see. So I think, that's where this presentation ends. So I think the best thing right now is I want to see everyone can download the Tor browser, because that'll be, so that you can test it out and see how it works for not just this link, but for every link in general. So yeah, let me quickly stop sharing this. Let me quickly stop sharing this, and let me share something else. So there is Discord. Okay, so next, where is, yeah. So here, this is where you can basically go to torproject.org and you can download the Tor browser for any of the devices that you're on. So I think if people can download it right now, that'll be useful. That'll be fun, yeah. So that we can test out a few basic websites and then see how they look. And I don't think there should be much of an issue in downloading this, because it works normally. So if people could test it out, that'll be cool right now. And if you have any issues somehow in downloading, just let me know. I'll give like 5 minutes. I think that should be enough to download Tor browser.
Kalyan, I think they have like 2 questions in the workshop channel.
Oh,
through that.
Yeah. Is there a reason why the normal method doesn't encrypt the device? Why it doesn't encrypt the destination and the source? No, it's just when traversing, the headers are not encrypted. It takes longer time to go from website to website that are encrypted, because it has to go from node to node, and then it has to, peel out the layer, read the header, and then go. So that takes time, but we, as people, want faster websites and things of that sort. So we don't encrypt the destination and the source are in the headers, basically. It takes time. So to speed it up, they don't encrypt it. See question. Okay, so are people able to get it downloaded? Okay. So once you download it here, let me. Oh, I'm going to leave Discord. It seems to be pausing the stream. Is there a way to change that? I don't remember exactly how to do that.
What's the problem?
Sorry?
Wait, what did you say the problem was?
When I leave Discord, it says the stream paused or something. Oh no, my bad. The stream's still run. Okay. Basically, here you can see how quickly Google works, whereas here in this situation, I don't know if people can see the. Is there a way to share the screen as I'm changing the website? Like if I want to go from Tor to a normal browser, will it notice a difference? Like to keep track of?
Instead of applications, do screens and then choose your screen.
Sorry? So,
are you just sharing like your Chrome right now?
Yeah, I think so.
Okay, do screen share, and then there's applications, and then there's screens, right? Share your whole screen.
Screens?
Yeah.
Oh, screen one. Okay, go live. Okay, so here, yeah, Google, fast. Here, Google. Oh, God. Takes slightly longer, and that is because it has to travel. Plus, also, if you notice, I got Google Germany, which is different than if you're in the US, because it basically the node in the situation is in Germany, so it's bouncing off of, so it ends up in Google Germany basically. And yeah, so if people have the Tor browser, we can. Let's see. Let me actually stop streaming here. Let's see. Time to find some links that work, like onion links that you guys can actually go to that are not bad.
Kalyan, I have a question.
Yeah.
What's the best website to search ourselves up to see, if we're on the black market or whatever?
What do you mean?
like how you search your name up on Google and then the results come up? How do you do the same thing on Tor, but there's more stuff on you? You know what I mean?
Yeah, I know what you mean. I haven't dabbled into that. I've done work on different things, so I haven't really Google searched my name in this situation. Let me actually look into it. Actually, 2 seconds. I am being blocked by. Okay, am I a robot? 1 second. Okay, so I'm trying to find the link. Yeah, I'm pretty sure this link is. Okay, so let me share screen. So one of the links is this. It looks pretty bad, but it's supposed to be a rent-a-hacker. It's not exactly a real website per se. It's mostly put up as like a joke kind of thing. But yeah, this is one of the website. It basically is built like a generic website for the thing, whereas so there's a lot of websites like this that are not exactly real websites, but they just are there as a mechanism for, I guess, catching people who want to do stuff. There's a lot of stories that happen about how people want to hire hitmen, but then it's usually just the police in the background. So there's websites like this where just basic websites that just catch people who are not that into it per se. And so, yeah, this is one.
It's still loading. I don't know if that's true for everybody else too.
Okay.
I can see it.
Oh, you can see it?
Oh, psych. Maybe it's just me then.
1 second. Can y'all see the link? Is something happening? Yeah. So, yeah, this is one of the websites which is, pretty tame. It doesn't exactly do anything, but, it's there. Can everyone see the link? Or can everyone see this? Or...
Yes, we can.
Okay, so yeah, so here you can see the link is a .onion site. And so this, for example, if run on here, won't work. Because these normal browsers are not used to dealing with these onion links and hence cannot work with these. So that's why, that's why if you want to go to onion links and things of that sort, these browsers are the way to go. I think that's mostly everything I have for today, honestly. There were a few other links, but then we figured out those links are not safe. So yeah, sorry, but that's where we're at. So yeah, that's my presentation for today. A lot of theory, I guess. And basically, if you want to have anything secure in any nation, you can check. You can Google, you can search a lot of things and get access to a bunch of sites through Tor. Yeah, I think that's the best way to go with it, is to say you can get access to things that you wouldn't have in a normal browser. So cool. That's it. Thank you for coming, everyone. It's a shorter workshop. Yeah, thank you. Yeah, I'm done.